I'm Choi Yun-Pui, Alvin, from Sha Tin Government Secondary School. I'm going to present my project titled On the Prime Number Theorem. In this project, I try to use some very elementary tools to analyze the PNT. My report is basically divided into 4 parts. And the first 2 parts is about some basic tools and definition, and the Selbert original proof. But today I will not go through the Selbert proof in detail. Instead, I will concentrate on the 3rd and 4th parts of my article. That is section 5 and 6, which talks about some of my observations and ideas about the prime number theory. Okay. First of all, prime number theorem states that pi x is asymptotic to x over log x, where pi x is the number of primes less than or equal to x. I find that, in fact, there is a very natural way to guess this formula. That is to use the inclusion-exclusion principle and the sieve of erratofinus. Using these 2 methods, we can obtain the formula. This one. As you can see that the left-hand side is pi x minus pi the square root of x. We can expect that the left-hand side is asymptotic to pi x. And we can also expect that the right-hand side is asymptotic to this one. That is, we remove the floor function. Then the right-hand side can using the Euler's idea, improving the Euclid's second theorem. That is to prove there is infinitely many primes. We can expect that the right-hand side is asymptotic to this one. As it is well known that the series on the denominator is asymptotic to this one. You can see that we have found a natural way to guess this formula. But notice that actually this deduction is wrong. This part is actually not asymptotic to this one. Also, this part is not asymptotic to this one. However, I want to emphasize that this way can really suggest us to guess the asymptotic formula. Okay. Using that equation, we can prove the Euclid's second theorem. That is, the number of primes is infinite. using some inequalities. Yeah. Also, we can use the prime number theorem to prove the generalization of Bertrand's postulate.
But let me ask you a question, right? Oh, sorry, I'll ask later. You have only 10 minutes. Sorry.
That is for arbitrary positive real C. We can find a positive KC such that this inequality holds. In particular, we have the Bertrand's postulate. That is, between n and 2n, there is a prime. Yeah. And using this fact, we can prove that prove an interesting result that n factorial is never a power of some number. Yeah. Okay. Session 6 is contains some phenomena I observed when doing this project. This session contains 4 conjectures. The first one is 2 asymptotic formula. The first one is this one. And the second one is this one. Personally, I think the first asymptotic formula is very interesting because we know that this one is asymptotic to this one. And we can prove that actually if our conjecture is true, then we will have the equality this one. So, to prove that this asymptotic formula, I think we may find the relation between this one for different m. Yeah. Although I cannot prove this asymptotic formula, I can prove a weaker one. That is why I think this asymptotic formula is important is that in Selberg's proof, he often used this asymptotic formula. He used it many times. So, and we can use this asymptotic formula to prove this one. But this one is stronger than this one. Yeah. So I think if we can prove this one, we may find, perhaps we can find a new way to view the prime number theorem. Yeah. And the second conjecture is about the generalization of Shapiro theorem. Yeah. We can use the Shapiro theorem to prove the prime number theorem.